I'm going to talk about spatial-temporal modeling, and of course, with an example of COVID-19 analysis that me and one of my current PhD students, Levin Gao, are doing for the state of California. Um, so before I just go there, just a quick important point. Why space and time? Well, it's basically the importance of where and when in statistics. Perhaps it's really not needed in this for this audience to actually go over the importance of this. We are all working with space-time modeling of some fashion, and I think the importance of the where and when in statistics has by now been well established, and in particular for infectious diseases as well. So when we think about space-time modeling, I'd like to say that this actually falls under one of four settings. And the first three are actually quite widely explored. So let's look at the first three very briefly. One is called what I like to label as continuous space discrete time. And this basically means that you actually want to interpolate at arbitrary resolutions of a space, which is why you treat space as continuous. That means at any particular location, no matter how fine that location is, that means it could be just a coordinate, a point, a latitude, longitude, or something like that. And you want to perhaps predict or interpolate your outcomes at that location. But the time is discrete. So that means it could be aggregated over a month or a year or a week or something like that. And so it's not as if it's evolving at a very fine resolution. It is in fact coming in discrete pockets or packets. And so an example is monthly temperature data. You can think about temperature existing everywhere in space. But when you're actually recording it, you're recording it probably as a monthly average or a monthly maximum or a monthly minimum. And so you basically get a summary over time. So time is treated as coming in discrete packets, whereas the space is continuous. There's a pretty substantial literature on this, in fact, and you can look at many papers. In fact, some of the speakers here in this conference have worked very much in this domain. Then you can look at continuous space, continuous time. This is an example where both space and time are in fact coming in at very fine resolutions, and you are interested in interpolation over space at arbitrary points and interpolating at time points or predicting at time points or for future data. So examples could be directional wind data. So these basically come in very fine resolutions, and the type of modeling that has actually been widely employed in these sorts of settings is to develop spatiotemporal covariance functions and use spatiotemporal processes to model them. Then the third one is discrete space, discrete time. And this actually has also been used very widely. In fact, Professor Andrew Lawson and Professor Lance Waller, who are both, I believe, participating in this conference. Dr. Lawson gave his talk yesterday. Actually have worked quite a bit on this, and this is also very useful, exceptionally important in epidemiology, and I think it is there are some very nice Markov types of models and other types of dependent models that have actually been developed in this domain. The fourth one is a little relatively speaking unusual, although that also is getting greater attention now, and in particular in the COVID-19 situation, when it literally came upon us rather suddenly, it has become very pertinent. And this I describe as discrete space and continuous time. Now, discrete space basically means that space is actually coming in as not at a very fine resolution, but in fact as aggregated spatial data. So for example, like the health summaries across counties, and then continuous time because the record of the health outcome is being in fact carried out at a very, very fine resolution, perhaps on a daily basis, perhaps even on an hourly basis in certain cases. And so the question becomes that, for example, here in California, we are interested in trying to model the daily COVID-19 hospitalization rates across the different counties. And how are we going to actually model this in almost real time, so that on a daily basis, the Department of Public Health, as well as the governor's office and all the other policymakers, can actually take a look at how the hospitalization rates are evolving. So discrete in general, when I describe it this way, usually refers to some level of aggregation. And as I said, the last category, I think, has arguably garnered relatively less attention, although again, I will say that there's been quite a bit of work that has been coming up over the last half a dozen years or so in this domain as well. Now, when we think about Bayesian modeling and statistical modeling and spatiotemporal modeling for infectious diseases, there are a few different aspects. And broadly speaking, I would like to say that there are the models that in fact try to account for the information that is provided through mechanistic modeling. And then there are the models that in fact are more purely observational statistical models that actually try to learn about the data as it comes in. And these are not necessarily completely disjoint, absolutely not. In fact, there's a very well-known term nowadays called Bayesian melding. If you have not heard about this, you can probably try to Google it, and you will find there's a fair bit of work, especially in the climate sciences, where this is being implemented. It was, I think, popularized by Adrian Raftery and his colleagues almost about a decade ago, but it has been used quite widely. I myself have been involved in Bayesian melding exercises for industrial hygiene and other types of public health exercises. The idea is that you have a mechanistic model. In infectious diseases, there are many widely used mechanistic models. We like to call these mechanistic models, but they're basically deterministic models of differential equations that try to explain a pandemic. You've probably seen enough of this already, and almost in every country, these are being used by departments of public health to try to predict what's going on. So there are these compartmental ordinary differential equations, and then there are diffusion models, and they basically try to say, well, at time zero, this is what we believe is going to happen. And then, there are other types of variants for these. There you can develop stochastic differential equations and processes. But the term mechanistic comes probably because it basically describes or tries to model through the language of mathematics, through the language of differential equations, through the language of rates of change, how the mechanism of this pandemic is going to evolve, or how the mechanism of this disease is in fact going to evolve over the population. And statistics has become particularly relevant in this because we learn about or train the model from the data over time, making use of prior information and observations into a single inferential framework. So this is a very, very nice exercise, and it is particularly useful because it is being increasingly shown that you actually can get better predictive performances using disease dynamics and statistical modeling. The idea about using statistics to learn about deterministic systems is relatively new still, even though it has been around for over 20 years. But, for a very long time, the role of statistics and applied mathematics was sort of a bit fuzzy because applied mathematicians used to like to swear by these models as the science, whereas the observed data would often be rather incongruous with the model. And what Bayesian melding has tried to do is try to retain the science and the mechanism that is being posited by the mathematical model, but yet updating it and training the model from the data. So we are actually involved in Bayesian melding for COVID-19. In fact, right now in my department of biostatistics at UCLA, we are getting data from the governor's office where we are trying to train these compartmental ODIs, such as the adaptations of SEIR models, to try to see how the evolution of the COVID-19 is looking in California. But I'm not going to talk about this today. That's a different talk, perhaps for a different time. What I'm actually going to talk about today is trying to understand the spatiotemporal dependence and the role of space and time in how the observations evolve. And in particular, I'd like to talk about a particular aspect in the management of COVID-19, which is about hospitalization rates. Now, you see, there are different aspects of the study of COVID-19, of course. I mean, there's the epidemiologic aspect where you're actually trying to look at the incidence of COVID-19. You're trying to look at the morbidity from COVID-19. And you've also seen in the media quite a bit about all the uncertainty surrounding this, and including the number of COVID-19 cases in a county or in a country or in the state, wherever you're looking at, because there are a lot of people who have not been tested, and a lot of tests may not have been done properly, and perhaps there's a lot of asymptomatic cases, and so on and so forth. So there's always a lot of uncertainty. But one point that is important is that hospitalization is a slightly better documented statistic. After all, you're coming into the health system, you're actually getting hospitalized, you have been diagnosed from COVID-19, and so at least you know the number of people who are hospitalized from COVID-19. Now, that does not mean that there are no errors here. Of course, there can be errors. There can be an underestimation of the number of COVID-19 positive cases in a particular place, and so on and so forth. But at least there is a documentation structure here. And in California, the data from the hospitals in counties across the state are sometimes available. In fact, in our case, it is available on a daily basis. So we are going to try to look at hospitalization rates. The other thing that is crucial in the management of COVID-19 is to say, okay, well, how long should the lockdown be there? Why do the lockdown? See, there's been a lot of controversy about the lockdown. Certain countries have actually not imposed lockdowns in as stringent a manner as certain other countries have. And this debate goes on as to what the effect of lockdown is, and so on. I think it is increasingly being shown in multiple studies that lockdowns have had a positive impact in terms of curbing the spread of the disease. But the important thing here is that hospitalization is a management issue, right? Because after all, even if there is herd immunity, and even if there is, even if some folks may posit that the lockdown is not needed, what if the disease is such, as in fact is the case of COVID-19, that a fairly steady rate of hospitalizations are happening, and our hospitals are getting crowded, and people are not being able to treat patients? That would be a catastrophic public health disaster, and that is what we need to avoid, and hence we want to look at hospitalization data. The other point I want to talk about is this discrete space, which basically in public health amounts mostly to what we call aerial data. And aerial data is basically regionally aggregated data. It could be at a county level, it could be at a zip code level, and so on. And it is by far the most common in public health, because point level information is usually unavailable because of data confidentiality protocols involving human subjects. So here, for example, I have an animation of this as well, but I think in the interest of time, I'm going to just not do this. This is a map of the recorded hospitalization rates per 1,000 positive cases for COVID-19 in California, starting from April 1st, which is about a couple of weeks or almost 3 weeks after lockdown was imposed in California, and all the way until literally last week, June 1st. And what you tend to see, so this the blues are good and the reds are bad. So the red, these are the counties, there are 58 of them, and you basically see that when you have the the redder the hue, then basically that means that there are some there's a fair bit of hospitalization going on. So you basically look at the positive cases for COVID-19. Now, of course, as I said, there could be some serious bias here. That is a different matter. But of the cases that are positive, how many are ending up in hospitals? Okay, that's basically what we are trying to look at here. So the denominator here are the positive cases, and the numerator, in some sense, is the recorded hospitalization, a number of hospitalizations. All right, and this happens across these counties on a daily basis, and we need to basically look at the trend. Now, even without doing any statistical modeling, just take a look at this map and you will see that things are getting better for sure, which is optimistic in terms of hospitalization. The maps are getting bluer and bluer as we go through time. What is interesting is to try to understand that, okay, is this trend that we are seeing really indeed because of the hospitalization rates and because we are able to control and curb the spread of the disease, or is there some confounding and so on and so forth, and how in particular are these rates affected by certain demographics and other variables? So we do have a fair bit of external like variables where we can try to understand some of the reasons why rates in certain regions are actually higher than others. And here you have the spatial distribution of some of the explanatory variables, African American, percentage of African American population, percentage of Hispanic, Latino, the gender distribution, senior citizens. Here's the population density. I do want to mention that San Francisco County is a very small county, but it is in fact one of the most densely populated counties in the whole of the United States. And you cannot probably see that here, it's somewhere out here, but it is actually substantially more densely populated than any of the other counties. Los Angeles County, which starts here and even goes all the way up to the San Diego belt, in fact is the largest, the highest populated county in the United States, but it is not as densely populated as San Francisco County is. And then there are certain other risk factors that you can have, such as smoking and so on. Now, these maps, now very often, what we tend to do in spatial temporal statistics, and a lot of the statistics literature tends to do it, is to say that, well, as statisticians, we like to put in these predictors, but then we really go into the process of the random effects and try to understand the distribution of the random effects, which is actually certainly a reasonable thing to do, because random effects certainly tell us a lot more about the residual variation that we are not able to explain away and can often generate new hypotheses and so on. But I should say that these maps also show and provide certain insights and show certain patterns. And the insights that we get, for example, are in certain cases. For example, when you see cases such as where there's a lot of spatial clustering of certain predictors, such as cigarette smoking, or even the demographic variables, such as the distribution of certain let's say African Americans or Latinos in the country, you can actually think about modeling by nesting the effects of some of these within the north, south, Northern California, Southern California, or something like that. It does make sense, so that you can actually prevent potentially deceptive or misleading impact of the predictors. So when we look at these things, the aerial maps and so on, we try to look at and try to ask questions such as, is there a spatial pattern? And then do we want to, in fact, smooth the data? And one of the things that becomes clear, in fact, you can do this through formal model fitting, as well as through other types of diagnostic measures, that simple IID random effects may not be enough. And so therefore, we really need to put some spatiotemporal structure into this. And the inferential aims for most purposes of aerial data are usually explanatory rather than predictive, because you, after all, are looking in terms of space, at least, because you are, after all, looking at a fixed state or a fixed domain of interest, a country or something like that. You have the politically delineated regions over which you want to focus your attention. And it becomes more like an iterative exercise by which to generate hypotheses and then test them, for epidemiologists and biostatisticians to work together. That is how this usually works. Because if there is going to be prediction, then we need to ask, is prediction even meaningful here? Because does it mean to actually talk about new aerial units? And one of the things perhaps that is close to predictions is that sometimes you might have missing data. So some counties, in this particular case, we do not at this point have, but initially there were some issues about missing data. So when you actually build a model, it is always nice to actually think about accounting for imputation. I wouldn't really call it prediction, but I would rather call it imputation, because you do have a region and you just want to basically try to impute the missing value for that, perhaps through the model. So that is the only thing that we need to keep in mind when we are actually thinking about what are the types of questions that we want our model to ask. Okay. Now, in our case, there is an interesting feature, which is that we may be okay with not doing spatial predictions, as is usually done with Gaussian processes or spatial process models, where you have a new location that comes in and you want to predict the value of your response, like temperature or pressure or some other climate variable or whatever you're looking at that new location. Here, it is not quite that, but we do have time. And there is certainly, given that it is coming at a very rapid rate, this data over time, over every day. In fact, if you want, you can even break up the day and go finer. But for this purpose of this talk, I'll just keep it at a day. And we need to actually perhaps provide some projections over time as to how the map is going to look into the future. And so for that, we actually need to basically make sure that our model is able to do that in a reasonably fast and fairly grounded manner, grounded in the sense that in a statistically principled manner. So the one thing to think about when you have a time resolution that is so fine is to actually think about aerially referenced space-time models. Again, there has been a fair bit of work in this area. In fact, Andrew Lawson has done some work in this area quite a bit. And then there's been a lot of diffusion models that have been done by, for example, Howard Rue and his team and so on. But basically, I'll just keep the matter simple here by saying that, well, let's look at y sub I of t as if it is the rate or the outcome or the count, whatever it is, that is perhaps coming from region I at time t. And this notation I use to basically bring out the fact that I'm going to treat this I being an integer index as discrete, whereas it can be looked upon as a function of time, because time is at a very fine coming at a very fine resolution. And then you actually try to model the mean structure here, plus you have the latent functional or spatiotemporal process with discrete space and continuous time. And then you have a measurement error noise process, as the case may be, which, for example, could be treated as normal distribution if you have converted this into a continuous variable, such as a rate or so on, and you've done your exploratory analysis to assume to make the assumption of a normal distribution not totally untenable. So this particular structure, the mean structure here, could include, let's say, epidemiologic variables such as you would have in a regression structure, but it could also be the solution to a system of linear differential equation if you indeed have a well-designed compartmental model for hospitalization rates in our case. And we have not done this for hospitalization rates, but if you're looking at the SEIR models and if you indeed want to understand the population dynamics, you can certainly bring in the differential equation into this spot. There are a couple of different ways of doing that. As I said, that's where the Bayesian melding literature comes in. You do have to be careful about how you treat these models. If you have, for example, linear compartmental models, then a Kalman filter type of discretization and a dynamic model based upon that usually works well. But the usual epidemiologic models that work well for a real data, and in fact are being shown to be working well for COVID-19, are not usually linear, they are non-linear. And that is where perhaps some thought needs to get into how you're actually going to do that. You could do perhaps sequential Monte Carlo and other types of dynamic models to approximate the nonlinear system of ODEs, or you could actually use higher order ODE solvers like the Runge-Kutta methods and discretize them and get a statistical model out of it. Or you could in fact simply pre-run the mechanistic model, the system of ODEs for a certain set of inputs, and then try to model the outputs of that model of the differential equation of the solution using a Gaussian process as an interpolator. So there are all these different techniques, and each one of these could be a different talk altogether. So I'm not going to talk too much about that, but it is, I think, an area where definitely a lot of research can be done and is being done, but there's a lot of potential to explore and find out more about how to accommodate mechanistic models into these frameworks. But I'm going to just basically keep this simple for now and focus more on this part, the ZIT, which is a region-specific stochastic process now, because I want to do predictions. Whenever you think about a stochastic process, basically a stochastic process for a Bayesian is nothing more than a prior on a function. And if you want to actually predict the rates at a particular time point into the future, or even infer about time at a fine resolution, that means perhaps there is a day when the data is not reliable and your collaborators, the epidemiologists and the health policy manager are saying, you know what, the hospitalization data coming in on these days are not reliable. Can we actually take the more reliable data and impute for those days? So then in that case, because this time is arbitrary and those days are arbitrary, you may actually want to certainly put in a process so that you can, after fitting the model in real time, in very quick fashion, predict the estimates of the YIT for those days and get a smoother and a filtered trend. Of course, you can actually cast this into a GLM framework where you would have the mean, and then you would have this process through a link function. And the key point is that these functions or these random functions are now going to be similar for neighboring eyes. That means neighboring regions, all right? So that's how we will need to build a model. Okay, now, when you think about this, you can collect over, since your space is fixed, at least for this purpose, California state, it's not changing, at least as far as I know. The counties are all fixed administratively. And so you can collect your entire your entire collection of random variables over the 58 counties of California and place them into your vector ZT. And then what you need is a multivariate Gaussian process that is basically going to be specified by what we call a cross covariance function. The cross covariance function is a matrix valued function, and its ijth element for any two time points, t and u, will be given by the covariance of ZIT and ZJU. And so if you really want to put a prior on the Z of t, a multivariate function, then you get to a multivariate Gaussian process. Now, this is very, very familiar in the context of multivariate spatial process models, in geostatistical models. Cross-covariance functions have been investigated at many, many levels. And Alex Schmidt, for example, who's here in this conference, has done some groundbreaking work in that area as well, among many others. And so the idea here is to actually model, let's say, for example, if you have two regions only, each argument in that matrix, in the elements of the matrix, will have a t and a u, and then the ijth entry is going to be just between the ith region and the jth region. So all we are doing is, in fact, instead of taking multivariate spatial processes where the multivariate comes from multiple outcomes, we are simply looking at the space, the regions as the multiple units, and we are simply forming the cross covariance matrix out of that. Once you have specified this, and I'm going to come to that in a second, then you are able to actually collect your realizations into a vector, and it will be a multivariate normal. Now, this Gaussian process is totally fine whether you have this model for the normal first stage or whether you have in a GLM, because you're going to hierarchically build this. So that is not completely unreasonable. But the important constraint that we need to build when we build this is that we need to bring in areal dependence into this, because as I said, in the settings of multivariate spatial processes for different outcomes, you don't have as much of a specified structure on the outcomes, so you want to be flexible and model them using models such as linear models of co-regionalization and so on. Here also we will take a similar approach, but we will need to make sure that this association in fact respects areal dependence. So areal dependence meaning that neighboring regions tend to be borrowing more strength from each other than regions that are further away. And so we will come to that, but once you have actually set up your covariance matrix for the realizations, modeling becomes very, very standard. You actually have a GLM type of setting here, could be normal, could be Poisson, could be binomial, depending upon the type of data you have. And this is over all space and time points. There should be a T sub j here and a T sub j here. That's a little typo there, I'm sorry about that. And then you have the distribution of the z's with a zero mean, and that covariance matrix that you will form through the cross covariance function. And then you place the priors here. So this is really fairly straightforward adaptation of multivariate spatial modeling into a space-time structure with discrete spatial regions. One other thing that you can do, and in fact we are doing this right now, is in fact looking at what is known as temporal rates of change. This is sometimes very, very useful to find because you basically understand not only are you estimating the random function, but you're trying to see how fast that random function is in fact changing over time. And the easiest way to do this, so there are multiple ways of doing this as well. One of the more sophisticated ways of doing this is to try to model the YIT itself as through the random function and build a stochastic differential equation out of it from the compartmental models. That's certainly a good approach, and it leads to certain classes of diffusion models. Another way, which is actually perhaps more relevant for this particular application of hospitalizations and so on, is that you actually take this random function, and you, after the fact that you have actually fitted the model, if the health policy managers and the hospital managers and in fact the government wants to look at the rate at which this is moving, COVID-19 hospitalization rates, then you can actually provide a summary of that. And all you do is basically form the derivative. You can do finite differences. The problem is numerical here with the h becoming small, and with these models becoming hierarchical models with a lot of random number generations and so on. Numerical robustness can become a little bit problematic in certain situations. So looking at the derivative and getting the distribution of the derivative, in fact, is a better and perhaps more robust approach. However, in order to do that, you need a little bit of stochastic calculus, not hard at all. Take the L2 mean square differentiability criterion for this process that we are looking at, and simply say that I'm going to model a covariance function. I'm going to build in the cross covariance function and use the smoothness of the cross covariance function to ensure that I have mean square differentiability in the realizations of this process. So the distribution theory is fairly standard. The smoothness properties of the realizations are going to be fairly standard and borrowed from what we already know from the theory of random fields and their smoothness. And the nice thing is that once you have been careful enough to model the cross covariance function in a way that these derivatives or this limit exists, the zi prime t naught, the derivative rather, sorry, not transpose, then the inference of the gradients becomes legitimate, because this particular multivariate process, zt and z prime t with the derivative of zt, is in fact a valid Gaussian process, multivariate Gaussian process, and that can be proved using standard techniques. There is a term for this which I like to use quite often. It's called wombling, looking at rates of change on spatial surfaces. Here we are doing only temporal wombling, meaning looking at smoothness and rates of change over time. And so the only thing you need to bring in is our good old friend, the Matern correlation function. After all, there's no better family that actually allows us to model the smoothness. And this parameter, the phi2 that you see here in this expression, in fact, will control the smoothness. And in particular, for example, if you take phi2 to be 3/2, then you can actually get mean square differentiability once, but not twice. So you don't over smooth unnecessarily, but at the same time, you can get your gradients. And then your cross covariance matrix can, in fact, look like this. It's a separable model, as you can see. You take this guy and multiply it with the graph Laplacian, which is basically what the car model does. And it's a proper car because the D is a diagonal matrix whose diagonal elements contain the number of neighbors that each region has. And the W is the adjacency matrix. In this particular formulation, most widely it is taken to be the binary one. But of course, you can actually define adjacencies in different ways and form that. And you can actually just put this in here. You get a cross covariance function. This particular guy models temporal correlation. So it is an adaptation of the Orsten-Uhlenbeck process so that we allow mean square differentiability. If this was half, it would have been the OU process. This would have become the exponential only. But the good news is that we have these nice closed form expressions for this, and the posterior predictive sampling can be done. Okay. All right. Now, one important point is what about the temporal dependence? All right. So this is one particular way of doing it, using a car model to bring in the cross covariance here. But we want to probably make this a little more flexible, and I'll tell you why. We want, in fact, a family of temporally indexed Markov random fields or other types of dynamically evolving aerial models. And let's go to Alex Schmidt's linear model of co-regionalization framework. And all we do is simply take that same framework. Nobody loves linear expressions more than statisticians do, given that we work with real data, and linearity certainly helps in computation and also interpretation. And we take the ZT to evolve as a linear transformation, perhaps temporally varying, for these latent factors or latent variables, latent processes. And these latent processes are independent. And if I do this, as long as each of these latent processes are independent, this is well defined by construction. And frankly speaking, for Bayesian modelers in particular, they love to go crazy, and they love flexibility. And so they can say, well, let's just keep all this temporally varying, and we will have a temporally varying covariance function or cross covariance function coming out from this. And so we can incorporate separability, non-separability, stationarity, non-stationarity, and so on in this framework. It's a very, very rich framework. But then there is this question that within a particular time point, all right, what should be the areal dependence? And obviously, one of the nice things is that, you already have a pretty big literature there. And say, for example, the CAR model or even the SAR model as an alternative relies on some variant of this graph Laplacian, right? But there are certain issues about this, like this particular rho parameter. People tend to interpret this as a correlation, and it unfortunately is not quite. And even if you do some simulations, you can see, for example, that simulated data with very, very high values of rho will hardly give you a Moran's-I, which is a nice descriptive way of evaluating areal dependence, not to be very high. Moran's-I about 1.0 would be high, but this is not even exceeding 0.5, even when rho is 0.99. And there's a very well-known paper by Melanie Wall, who was my former colleague in Minnesota, but she's right now in Columbia University, where she actually explained how the rho cannot be interpreted as a correlation between neighbors. Now, folks often do not care about the rho as much. in many cases. In fact, in many cases, they use the ICAR, where the row is set to be equal to 1, and they don't worry about the propriety. But the thing is that in these sorts of models, where you need the temporal process itself to be validated, if the spatial process itself becomes singular, right, through the singularity of this matrix, then the spatio-temporal process, unfortunately, is going to become singular as well. So we do not have the luxury of using the ICAR in this particular setting as we have in certain other settings. There's a nice paper by Sancho and Krensky before borrowing on this also about why the row's interpretation becomes problematic. So we bring in the row, and if we bring in the row, well, then we better interpret it. Otherwise, it's going to become complicated. And especially in the context of where, you know, some of the outputs or some of the analysis of the statistical models could become could perhaps be used in mechanistic modeling, then we want to know and provide a strength of the spatial autocorrelation parameter. So one of the things that we can look at is, instead of doing a graph Laplacian type of model, we can look at a directed graph, and we can try to look at extend work that has been done not so long ago by one of my former students, Abi Datta, in his dissertation called DAGAR, directed acyclic graphs, and we can extend them to spatiotemporal DAGARs. And what we do is, let's come back and just look at this guy, this particular fella, the linear transformation that will basically govern the dependent structure on the ZT. And as has been beautifully portrayed by Howard Rue and Leo Held in their wonderful book, it's always better to look at the precision matrix. So let's look at the Cholesky factor of the inverse of AT rather than AT itself. And if you actually decompose or model, I should say, I'm going to model this AT through a conditional dependence directed graph, then you can get a structure such as this. And f of t is a diagonal with precision matrices. They are conditional precisions. And the b of t become related to the partial correlation coefficients or the conditional regression coefficients of the model as we move through the graph. The nice thing is that the quadratic form that is needed and the determinant that is needed do not need any type of matrix algebra. So especially for scalability, and given that, you know, here the scalability is not so much in terms of space, but in terms of time, that a lot of temporal data is coming in at very fine resolution, the best way to use linear algebra is not to use it at all. And this is nice that we can get this closed form expression and proceed with that. Now, how do we model the B and the F? Because if we do this, then we will get a valid A, and the model will be valid. We don't need to worry about positive definiteness. So here is where some of this, the structure comes in that gets into a little bit of technicality, but I will refer to the original paper, which appeared in Bayesian Analysis in the December issue of 2019. Basically, what we do is we say that, okay, when can we actually construct positive definite kernels on a graph? And this answer is actually a pretty interesting answer. There's a lot of work recently being done in machine learning in other contexts as well. But the easiest answer is if you have a tree. If the graph is a tree, then you can actually construct a valid autoregressive AR1 model on the tree. Okay, and that is very easy to do. Now, obviously, California is not, the map of California will not give you a tree when it comes to the corresponding neighborhood graph of the based upon its counties. So we need to basically extend that from a tree. But the way we do that is we actually take the regular graph, a loopy graph perhaps, and then we decompose it into a disjoint union of what are known as embedded spanning trees. And embedded spanning trees are trees that basically, if you take the union of those trees, no edge is lost from the original map, and yet you have each component of that graph as a tree. And if you now build an autoregressive model for each of those trees that constitute the entire graph, then you get a very simple structure for these coefficients. And they turn out to be in closed form with this row. And the precision also comes out in closed form. And now you can really say that, you know what, I can actually do time varying models even for the row, the spatial correlation. After all, each time point gives me a spatial snapshot of the map of California. There's no reason to impose that the spatial clustering at each time point will remain the same. In fact, it does change, perhaps not a massive lot, but it does change. So we can easily build in the row of t here without making our life too complicated, because after all, it's only one real valued function of time that comes into the modeling. All right. And we can put in priors on this row of t as a functional prior. It could be a Gaussian process itself, or it could be just over, since we have the resolution over discrete space, we could just put a IID prior for each time point. So there's a flexibility in modeling of the row t. But the determinant doesn't change, and we still get that in closed form. The quadratic form still evaluates like that. There is positive definiteness guaranteed for any row between 0 and 1, and the row is interpretable as a correlation parameter. So that's basically what we do. But there is one issue, that when we do a directed graph, and then when we actually decompose that graph, there is the ordering of the graph. And the model becomes specific to the ordering of the graph. And so how do we actually overcome that, or how do we in fact deal with that? Okay, because every ordering will yield a different model, and that's just going to blow up. There are so many models. Are we going to now compare them? There's no particular reason why there should be one order that should be preferred over the other. So a natural question to ask again is to actually look at if we can average over the Cholesky decompositions of these precision matrices. And the beauty of this is that indeed we can. And if you look at this as a precision matrix, and you take an average over this NS factorial, NS is the number of counties, number of spatial units, and average over all permutations of that of the ordering, you actually get closed form expression for the QT up to 2 scalar functions f and g, which are not too cumbersome, in fact, to compute. And the interesting thing is that the diagonals of the precision, the conditional variances, depend on first order neighbors, whereas the off diagonals depend upon second order neighbors, Markov dependence. But they can be characterized completely through this. The nice thing is that when you actually, this is a simple simulation example, just to show you the interpretation of rho. If you look at the straight path graph, which is like over time, then you would simply get a straight line for the DOG-R, or the order free DOG-R. We call the averaged ordered as order free. And both these give very, very close to 45-degree lines. So the association between rho, the parameter rho, and the correlation interpretation of this is quite good. Now, of course, things are not as perfect as the graph becomes more irregular. In a grid graph too, it's very, very nice, quite good. But if you look at, let's say, a map of USA where we did the simulation, it does get a little bit off the 45-degree line. But still, it is always better than, for example, the interpretation of a proper car. So in terms of the spatial clustering, that's what we do. Now, in this framework, we now proceed and we fit our model. You can use this model is agnostic to your to the exact algorithm that you want to use. So if you like INLA, you can use INLA. If you like Hamiltonian Monte Carlo, you can use that. If you like plain vanilla Markov-Chain Monte Carlo with random walk metropolis, that's also possible. So all of this is a Bayesian model. Once you formulate that, you can do it. It's very, very scalable, especially over time, which is of interest to us here because of the structure that I showed. The determinant and the quadratic form coming up in the Gaussian comes in closed form. And you can even average over orderings. And even then, the scalability, although gets a little diminished, not that bad, because the precision matrix is available in closed form up to scalar functions. Sparsity is ensured by selecting the neighbor sets, and in aerial maps that comes out. Here you have the posterior estimates of the spatial correlation parameter as we go through time. So as you can see, we can provide this over time in a fairly robust manner. And then you can, of course, look at the gradients. Well, we are actually, I don't have the map of the gradients here. We are working on that right now because there are some new data are coming in. We will present that to the governor's office and the California Department of Public Health once this is completed. But you can look at these the hospitalization rates adjusting for some of the risk factors, and indeed in two of the largest counties in the state, both these pictures indicate a happy trend in that it is in fact substantially coming down. And this is where health economists and policy makers come in as well, and they basically say, okay, look, are we in fact doing well in terms of managing the cases? Hospitalization is about managing the cases, treating people, and so on and so forth. And indeed, the stress on the hospitals are certainly going down. And this of many things, I would say that lockdown certainly has massively eased the impact on the hospitals in terms of treating patients. Here are some of these explanatory variables. No surprise that African Americans and Latinos have been much more adversely affected by this. This very, very unfortunate healthcare system, in my opinion, where folks from certain communities certainly do not have the access to healthcare. Many of them are uninsured. Many of them don't go to the hospitals. Remember, this is impact on hospitalization from COVID. So these are people who actually have tested positive, but have not actually gone into hospitals. Interestingly, this is something we are seeing. We need to look at it a little bit more closely. The number of hospitalizations is quite substantially different between males and females. And it is somewhat congruous or consistent with data where we are seeing that a lot of males, in fact, are getting much sicker than females through COVID-19. But before reading too much into this, this needs to be looked at, and we need to, as I said at the very beginning of my talk, there are certain factors about the spatial distribution of some of these variables, and we need to see if certain nesting models or nested models will bring this picture better, make it more clear for us. Smoking is interesting. If you look at the incidence rates for COVID-19 and smoking, there really is not as much of an association. There have been certain studies that have been that have shown that there's really not that much. But when it comes to hospitalization, again, we are seeing it seems that if you can get way sicker if you actually have this if you are a smoker from COVID-19, even though it may not substantially increase your risk of getting COVID-19, your risk of getting into a hospital because you're a smoker may actually be maybe increased. So again, there's some work that needs to be done. So I think I'm just getting out of time, and so this is thankfully the last slide for all of you. I'll just summarize. We have these spatiotemporal DAGAR models for aerial data that have been constructed, and what we have done is we have constructed sparse Cholesky factors, borrowing ideas from Markov random field modeling, directed acyclic graph modeling, and linear models of co-regionalization. The important thing is that we have modeled space discretely so that we get a family of aerial models, but continuously evolving over time. You could, if you're not interested in gradients, model time using Orson-Uhlenbeck processes. These give tridiagonal precision matrices and even further scale up. But they're very, very numerically robust as well. But if you want to do gradients and temporal gradients, as I said, you need a little bit more smoothness. So you need to adapt with the midterm. And then you can actually also look at the model space using DAGAR, meaning if you don't want to do the order-free DAGAR, the average DAGAR, and retain the interpretability of the ordered DAGAR, you can actually do, as Bayesians like to do, model averaging over the space of all NS factorial models. It's a large space, but it's interesting to see what is going on there. We are ensuring scalability for large aerial data particularly over time. Aerial data in general over counties, the graph Laplacian models or the DAG-R models will always yield sparse precision matrices. So that is a less of a concern over space scalability, but over time we are ensuring that. And then finally, we are seeing definitely better model fits than some of the car models for many of the scenarios. So I think on that, I'm going to end my talk, and thank you very much for your attention.